Hi everyone, welcome to part 3. So in this part we're going to talk about um, independent Q learning, short for IQL. So far you should have enough foundation to understand what is independent Q learning is. And then we're also going to talk about some of the challenges that we're facing combining independent Q learning with a deep neural network for multi-agent settings. So let's go. So in this paper, we consider our environment as cooperative multi-agent in partially observable setting in which each agent has their own action observation. What does this mean? I have no idea. Let's go figure out. So imagine you're playing your agents. Each of your agents are playing Dota game. This is agent A, have different character, and this is agent B has their own characters. So each agent have their own neural network that approximate their Q value or action values. And they have their own observations and they take their own actions. So like each agent have their own opponent, they're fighting against their own opponent, and they see like perceive like different part of the our game space here. So but at the end, all of them they cooperate with each other because they're sharing the same reward. They want to win against like other opponent. So at the end, they're sharing the same reward, but even they have their own action observations. That's why we use it independent Q learning. We also mentioned independent Q learning is more scalable because it's just much easier for like we understanding over each of the agents action observation, whether they have like joint action observations, the explanation I mentioned for paper in the classroom. So here, something worth to understand. So instead of like we have a queue function here, and we use like state and actions, but instead we're using T A and UA, and it means like instead of like T here means agent action observation history. The reason we use agent action observation history, guess what? It's because we have partially observable setting. That's why we use agent action observation history. Um, and then we also use like U as like agent action. So it's kind of like a other like annotate like ways of like demonstrating A is like the same. And that's for agent A. You can have for agent B, for agent C, whatever you have. And this is for partial observable setting. And if you have fully observable setting, those are going to be the same. So we use like a state and action. So kind of like consider as like the same. The properties of like IQ are with like deep neural network. So it is scalable because we like mentioned they have their own independent action observations agent, so they're scalable. But it's not a stationary. What is not a stationary means? I have no idea. Well, non stationary means like every time you're trying to learn about your environment and your agent they have actions and drawing particular observations and they learn the policy based on that action and mapping to that based on that observation mapping to the actions they learn the policy. But the dynamic of your environment is changing because you have a bunch of different agents every time they change their like actions, so you cannot really like figure out what is going on to my environment. So every time like you're learning particular like policy, but your environment is changing because each agent learning their own policy. So the dynamic of environment is constantly changing. Therefore, your environment is not stationary. So you have no idea like the policy you're learning is going to be good at all. So let's understand some math. That's like a main problem we have in multi-agent reinforcement learning when we try to apply with neural networks, which is not stationary. So some more annotation. I have it in my blog. You can read through it more specifically. And here are loss function, given the parameters, and we had that like we described that like you kind of like understand the same loss you see it in like our for DQN. Um, so And that was one of the reasons that we were like trying to figure out why it's not a stationary. So when you have your policy given a state, your policy is kind of like rely on policy of like all other agents. But because your policy of all other agents is changing, so those two are not similar for your next states. So therefore, you have like a stationary problem. That's all about it. I'm gonna see you how we resolve non-stationary problem in the next video. Bye for now.